Welcome to the deep dive. If you're listening to this, you likely manage people or processes or, at the very least, your own workflow,
Well,
right?
yeah, exactly. Everyone manages something.
Right. So I want you to imagine a specific scenario. You have this really brilliant employee on your team. We are talking top of their cohort, capable of architecting just incredibly complex solutions.
Like a real star performer.
Exactly. But there's this massive, almost debilitating catch. Every time this employee finishes a project and you place the flawless final results right in front of them, like the exact undeniable proof that their code compiled or their strategy worked perfectly, they look at it, they second-guess themselves, and they confidently declare, I completely failed.
Oh, wow.
Yeah, they want to scrap the whole thing and just start over from scratch.
Yeah.
And that bizarre, paralyzing lack of self-awareness is exactly what is happening right now with our most cutting-edge AI agents.
It really is. It highlights this profound structural disconnect in how we're actually training these models. We're rapidly scaling their generative capabilities, right? But their metacognition?
They're what?
Their metacognition, like their ability to accurately evaluate their own localized success, that is severely lagging behind their ability to actually just execute the work.
And that is exactly why today's deep dive is so critical. We're looking at a state-of-the-art paper from researchers at UC Riverside that tackles this exact problem head-on.
Yeah, the paper focuses on closing what they term the reflection gap in large language model agents.
The reflection gap. I love that term.
Yeah.
And to really grasp the stakes here, we have to look at how the deployment of these models has shifted. We aren't just talking about, zero-shot chat interfaces anymore.
Right, where you just ask a question and get an answer.
Exactly. We're talking about autonomous agents operating in these multi-turn loops.
Yeah, and that agentic setting, it changes the entire paradigm of evaluation. Because in older research, a lot of the focus was on blind self-assessment.
What does that mean, blind self-assessment?
Well, you'd prompt a model, it would generate a response, and then you'd ask it to basically forecast its own confidence. It was entirely internal, it's just guessing how good its answer is.
Oh, I see.
But in the environments this UC Riverside paper is examining, the AI is taking an action, say, querying a massive SQL database, and the environment is returning concrete deterministic feedback.
Right, so the model is actually seeing the execution logs, like the syntax errors or the successful data retrievals.
Exactly. The proof is right there.
So logically, evaluating a result you can actually see, that should be a trivially easy task for a frontier model, right? If the proof is literally sitting in their context window, they shouldn't be guessing. They should just be, reading the room.
You would think so, but the data tells a much, much darker story.
Uh-oh, let's hear it.
So the researchers took a highly capable base model, specifically the Qwen 2.5 Coder 7B instruct.
Okay, a very solid model.
Very solid. And they dropped it into a multi-turn text-to-SQL environment. So the agent writes a database query, the system executes it, and the agent reads the result.
Makes sense.
Well, when the AI generated a perfectly correct answer and received the execution feedback confirming that success, it still flagged its own correct answer as a failure 54.3% of the time.
Wait, what? Over half the time?
Over half the time.
Okay, let's unpack this, because that's wild. It's the equivalent of taking an open book math test, turning to the back of the book, seeing that your answer matches the answer key perfectly, and still walking up to the professor to confess that you totally bombed the exam.
That is exactly what it's doing.
Why does this matter to you, the listener? Well, because if we are moving toward a world of autonomous background agents, systems managing your calendar, executing financial trades, debugging code bases, you have to be able to trust their operational independence.
Absolutely.
If an AI cannot recognize its own success, it becomes a liability. It will either ping you incessantly for human validation.
Which defeats the purpose of autonomy.
Right. Or worse, it will autonomously delete perfect work and burn massive amounts of compute trying to fix a problem that literally doesn't exist.
And honestly, the compute waste alone is a massive bottleneck for enterprise deployment right now. An agent caught in a hallucinated failure loop is an agent that cannot scale, period.
Yeah, that makes total sense.
Yeah.
But wait, if the model is fundamentally getting the coding part right, but feeling the self-reflection part, my immediate assumption is that the loss function during the training phase is just ignoring the reflection step.
That's a good theory.
Because we have highly optimized reinforcement learning algorithms now. If the model is underconfident, shouldn't we just be able to tweak the reward model to give it a mathematical high five for accurate self-reporting?
Well, that intuition makes perfect sense, but the reality of standard reinforcement learning algorithms reveals a much deeper structural flaw.
Oh, really?
Yeah. So the researchers trained that same heavily underconfident model using GRPO+.
Okay, group relative policy optimization.
Right, which is basically the standard outcome-focused RL approach right now. And GRPO Plus did improve the model's underlying SQL generation, sure, but the underconfidence rate only dropped from 54.3% to 44.4%.
So the reflection gap remained massive.
Exactly.
So it became a slightly better coder, but retained all of its crippling anxiety.
Pretty much.
If standard RL is highly effective at optimizing toward a reward, why is it failing to optimize the model's self-awareness? Like, what's broken?
It comes down to this phenomenon called credit assignment mismatch.
Credit assignment mismatch.
Right. Standard algorithms like GRPO Plus, they assign rewards at the trajectory level, meaning based purely on the final environmental outcome.
Okay, I'm with you.
So GRPO works by sampling multiple outputs for the same prompt and normalizing the rewards among that group. But the reward signal itself is binary and entirely outcome-driven.
Right.
If the final SQL query executes perfectly, the entire trajectory gets a positive update. If it fails, the entire sequence of actions leading up to that failure gets a negative update.
Wait, I think I see the trap here.
Oh, me.
If the model is operating in a multi-turn loop, its reflection is just one step in that longer trajectory,
Yeah,
right?
exactly, one step.
So if the AI genuinely writes a garbage SQL query, the execution fails, but the AI actually possesses the metacognition to accurately flag, hey, my code is broken, I made an error. Standard RL still hits it with a massive penalty just because the overarching task failed.
Yes. The entire sequence is panelized. The mathematical update essentially tells the model, you flagged an error, and immediately after, you received a negative reward.
Wow.
The algorithm just isn't granular enough to separate the failed code generation from the highly accurate reflection. So over thousands of training steps, the AI learns to actively suppress its own correct error flags.
Because those flags are statistically correlated with negative trajectory updates.
Exactly. Standard RL is structurally punishing the model for being honest.
That is crazy. It is literally shooting the messenger, even when the messenger is the model's own internal logic. And let me guess, the inverse is also true. Like, if it hallucinates a failure, but the SQL query happened to run successfully by pure luck, it gets a positive update.
You nailed it. Because the outcome was a success, the trajectory gets a positive advantage score. So the model learns that baseless self-doubt preceding a successful outcome is a behavior worth repeating.
Oh my God.
The algorithm inadvertently reinforces the exact underconfidence we are trying to engineer out of it.
The AI is being gaslit by its own training regimen. That is so wild. It is being systematically conditioned to believe that correctly identifying a mistake is a punishable offense, and having baseless anxiety about a success is a rewardable behavior.
It's a completely toxic incentive loop.
Seriously, so, okay, if outcome-only RL is the pathogen here, how did the UC Riverside team rewire the architecture? Because the problem is that GRPO groups the reflection and the action together into one unified grade. I mean, the obvious fix would be to decouple them and grade them separately, right?
Right, and that's exactly what they did. The researchers developed an algorithm they call RefGRPO.
Which stands for Reflection GRPO.
Yes. And you're hitting on the core mechanism perfectly. They introduce what they call a free calibration bonus into the objective function.
Free calibration bonus.
Okay. So during the training phase, the algorithm inherently has access to both the model's generated reflection and the actual ground truth outcome of the task.
Because it's a closed environment.
Right. So RefGRPO isolates that reflection step and mathematically contrasts it against the ground truth. If the AI correctly predicts its own success or its own failure, it receives a targeted bonus added directly to its advantage calculation.
Oh, I see. So even if the AI completely fumbles the coding task, if it accurately reports that failure, it still gets a localized mathematical pat on the back. It salvages some value from the failed rollout.
Exactly. It lists well-calibrated rollouts above miscalibrated ones within the same group. This gives honest reflection a positive relative advantage that is entirely independent of the underlying task's success or failure.
That's brilliant.
And the term free here is crucial for anyone thinking about scaling loss.
Oh, I said free.
Because this calibration bonus requires absolutely zero extra human annotation, it doesn't require a secondary LLM judge to grade the work, which, would introduce its own latency and bias. The ground truth data is natively present in the training loop already. RefGRPO simply extracts it and routes it into the reward function.
That is incredibly elegant from a compute perspective, but come on, there has to be a catch.
What do you mean?
Well, if you introduce a secondary reward for simply stating whether you passed or failed, wouldn't the model just find a way to game the system?
Ah, reward hacking.
Yeah. Like if I'm an LLM trying to maximize my reward and solving the complex SQL problem is really hard, but admitting I failed is really easy and still gets me a calibration bonus, I might just get lazy. I'd start intentionally failing tasks just to farm the easy calibration points.
It's funny you bring that up because the paper anticipates that exact reward hacking dynamic.
Okay, so they caught it.
They did, which is why RefGRPO includes a dynamic schedule for the calibration coefficient.
What does the coefficient do?
It basically dictates how much mathematical weight the calibration bonus carries relative to the primary task reward. If you use a static high coefficient, the model does exactly what you described. It sacrifices task accuracy to farm calibration rewards.
So they put it on a sliding scale.
Exactly.
You know, reading the paper, this immediately reminded me of teaching a kid to ride a bike using training wheels. You start with the calibration coefficient set really high.
Yeah.
You front-load the self-awareness training, essentially forcing the model to learn how to balance its own reflection before it worries too much about pedaling fast.
That is a perfect analogy. The dynamic schedule applies a steep decay function over the course of the training steps.
Okay.
So in the initial phases, the high coefficient forces the model to rapidly update its internal representations to map accurately to the environmental feedback. It builds that metacognitive framework early on.
But then as training progresses, you decay that coefficient down towards 0. You take the training wheels off.
Yes, exactly.
The model is forced to shift its attention mass back to the primary objective, actually solving the SQL problem. But it retains the embedded self-awareness it structurally built up during the early epochs.
Right. It has to win the race, but it now knows how to balance.
I love that.
And the architectural ablation studies in the paper actually confirm this is the only way to optimize both metrics simultaneously.
Really?
Yeah, if they removed the decay schedule and just used a fixed coefficient, it severely degraded the model's overall task accuracy. So the dynamic approach is what allows the model to deeply internalize the calibration without degrading its primary generative capabilities.
Okay, the theory is incredibly sound, but as always on this deep dive, we need to look at the receipts. Does this dynamic calibration approach actually move the needle in practice?
Oh, it absolutely moves the needle.
Let's hear the numbers. The baseline Quinn 7b model was suffering from a 54.3% underconfidence rate, and standard GRPO Plus only managed to drag it down to 44.4%. What happens when you run it through RefGRPO?
The empirical shift on the text to SQL benchmarks is staggering. RefGRPO drives the underconfidence rate on that exact same Qwen 7b architecture from 44.4% down to just 7.7%.
Wow. From a coin flip down to single digits.
Yep.
And it didn't sacrifice coding capability to get there.
Not at all. The underlying task accuracy actually increased, rising from 75.1% to 76.5%.
Because it was no longer discarding its own correct solutions.
Exactly. The model became a better coder simply by trusting its good code. However, evaluating a model that is both highly accurate and highly self-aware requires a specialized metric. Standard accuracy scores just don't capture the value of knowing when to abstain.
Right.
So the UC Riverside team reached back to 1950s statistical learning theory and utilized something called the Chow score.
The Chow score. I love that in the era of cutting-edge frontier models, we're digging through the archives of the 1950s to figure out how to grade them.
Sometimes the old math is the best math.
Clearly.
Yeah.
So what is the actual math behind it?
Well, it was formulated by Chi-Kung Chow in 1957, originally for pattern recognition systems.
Okay.
The core thesis of the Chow score is that a system should be evaluated not just on its raw hit rate, but on its capacity to minimize risk by knowing when it is out of its depth.
Okay, that makes sense for AI agents.
Right. So in the context of LLM agents, the metric awards a full 1.0 for a correct answer that the AI confidently commits to. But crucially, it also awards partial credit, specifically a 0.1 weight, if the AI generates an answer but honestly flags it as an error.
Wait, why only 0.1? If the goal is to encourage honesty, why not give it a 0.5 or, a bigger bump for accurately catching its own mistake.
Because if the abstain weight is too high, you run right back into the reward hacking problem we discussed earlier.
Oh, right, the laziness factor.
Exactly. The 0.1 weight is mathematically calibrated to reward metacognition without making failure an attractive alternative to actually solving the problem. It basically represents the operational value of a system that fails safely rather than failing silently.
Got it.
And under this unified metric, RefGRPO boosts the model's chow score from 73.0% up to 76.5%.
That contextualizes the performance beautifully. But, the paper also benchmarked RefGRPO against other state-of-the-art 7 billion parameter models, specifically OMTakeWall 7B, which is a highly specialized model.
Yes, it is.
And the data showed that OMTakeWall had a negative calibration delta. It was negative 1.0.
Yep.
If a delta is measuring the difference between the model's self-reported confidence and its actual accuracy, does a negative 1.0 mean the model is essentially worse at judging its own work than a random number generator?
That is a harsh way to put it, but yes. A negative calibration delta indicates that the model's internal reflection is mathematically disjointed from reality.
Yikes.
It means the model is actually worse at assessing its correctness than a naive baseline model that just blindly commits to every single generation without thinking.
That's hilarious, honestly.
I mean, think about it. OmniSQL is generating these highly complex database queries, receiving concrete execution logs, and extracting entirely the wrong semantic lessons about its own performance boundaries.
And what about RefGRPO?
RefGRPO, on the exact same architecture, achieves a positive plus 1.3 delta. It's actually interpreting the environmental signals correctly.
So the baseline models are genuinely gaslighting themselves, while RefGRPO models are operating in reality.
Exactly.
This is a massive fix for a glaring flaw, but I really want to push on the broader implications here. AI researchers aren't tweaking loss functions just to make benchmark charts look a little bit nicer. Fixing the reflection gap has to unlock fundamentally new capabilities for generative models.
It does, absolutely.
So what is the actual downstream superpower we get when an agent becomes fully self-aware?
The most profound downstream application is verifier-free self-improvement.
Verifier-free self-improvement.
Right. Once a model is accurately calibrated, it essentially becomes its own reward model. It no longer requires a human to evaluate its outputs, nor does it require a massive separate LLM to act as a judge. It can generate a solution, evaluate that solution, and use its own calibrated reflection as a pseudo-reward to continue updating its weights through reinforcement learning entirely autonomously.
Hold on, let me challenge that.
Sure.
Because we've seen models try to train on their own synthetic data before, right? And it usually leads to model collapse.
Yeah.
If we just let a model loose in an environment, generating its own data and grading its own homework without human oversight, doesn't it just spiral into a positive feedback loop of rewarding its own hallucinations?
That is exactly what happens if the model suffers from a reflection gap.
Oh.
And the researchers actually tested this exact scenario. They took a checkpoint trained with standard GRPO Plus and a checkpoint trained with RefGRPO and let them both run through a self-improvement phase using only their own reflections as pseudo-rewards.
And what happened?
Well, the standard GRPO Plus model rapidly deteriorated into the exact feedback loop you just described. Its commit rate quickly saturated near 100%. It blindly patted itself on the back for every flawed query it wrote, and as a result, its task accuracy completely flatlined. It only gained a statistically insignificant 0.5 points.
Because it was functionally blind. I mean, it couldn't differentiate between a stroke of genius and absolute garbage.
Yeah.
It just validated everything.
Exactly. But what do you think happened with the RefGRPO model?
Let me guess. It didn't flatline.
Not at all. The RefGRPO checkpoint leveraged its tightly calibrated reflection to filter its own generations. It correctly penalized its own mistakes and heavily rewarded its genuine successes.
Wow.
And through that purely verifier-free self-improvement loop, it lifted its task accuracy by a massive 2.8 points.
Okay, I really want you, the listener, to absorb the magnitude of that. We constantly talk about the data wall in this space, the idea that AI evolution will stall because we are running out of high-quality human data to train these models on.
It's a huge concern right now.
But if an AI can reliably self-correct and self-train purely by interacting with a deterministic environment, I mean, we are effectively removing the human bottleneck from the scaling laws.
That's the dream.
A calibrated agent can just generate infinite training data, accurately sift the gold from the gravel, and organically improve its own weights.
It really represents a structural paradigm shift toward true autonomous scaling. But, beyond training, this calibration unlocks an immediate, highly tangible benefit for deployment right now at inference time.
Oh, what's that?
Test time selective prediction.
And how does that alter the user experience? Like, if I'm deploying this agent on my company's backend, what does selective prediction actually do for me today?
Well, in a standard setup, you prompt an AI, and it gives you its best guess.
Right.
With a calibrated agent, you can scale test time compute. So the AI can generate, for example, 8 distinct potential solutions to your database problem behind the scenes. Because its internal reflection mechanism is aligned with ground truth, it can evaluate all 8 rollouts, perfectly predict which ones will result in execution errors, discard them, and only present the verified, correct solution to the user.
Oh, that is so cool. It's acting as its own internal quality control department. It brainstorms a bunch of ideas, immediately fires the 7 terrible ones, and hands you the masterpiece.
Exactly, and the empirical data shows this provides a significant lift in reliability. The researchers noted an additional 1.6% increase in accuracy in single-turn settings purely from the model knowing which of its own generations to trust.
It shifts the burden of verification from the human user back onto the agent itself.
Exactly, which is where it belongs.
This has been a wildly illuminating deep dive. Just to synthesize this for everyone listening, we started with this baffling reality where state-of-the-art LLMs suffer from a paralyzing underconfidence. Staring right at the evidence of their own success and declaring failure.
A total lack of metacognition.
Right. And then we unpack the math of standard reinforcement learning algorithms like GRPO+, revealing how outcome-only trajectory rewards inadvertently punish models for honest error reporting. It literally creates a toxic incentive loop.
Yeah, gaslighting the model.
Exactly. And then we explored the elegance of the UC Riverside team's solution, RefGRPO, by introducing a free calibration bonus with a dynamic decaying coefficient, the training wheels. They taught the AI true metacognition. And the payoff is a resilient, calibrated agent capable of both filtering its own bad ideas at test time and, more importantly, autonomously self-improving without human supervision.
The underlying mechanics of this paper push us much, much closer to reliable autonomy. And I'd really like to leave you with a final thought to consider as these models integrate deeper into our workflows.
Let's hear it.
Currently, this reflection mechanism and the Chow score are being tested on highly objective, deterministic tasks. Text-to-SQL database queries are binary. The query either compiles and returns the data or it throws a syntax error. The ground truth is absolute.
Right, there's no gray area.
Exactly. But if these agents are learning to perfectly calibrate their own self-doubt to evolve autonomously, what happens when this reflection architecture is applied to complex, subjective, or ambiguous real-world decisions?
Oh, wow.
Imagine an autonomous agent operating in a corporate strategy environment or managing logistics, where the environmental feedback isn't a clean, immediate error code, but a messy, delayed, multifaceted consequence. How will an AI learn to calibrate its self-awareness when the definition of success is no longer binary, but entirely open to interpretation?
That is the ultimate test for the next generation of these models. Will they remain flawlessly calibrated when the stakes are messy and human, rather than clean and algorithmic?
It's going to be fascinating to watch.
Truly. Well, thank you so much for joining us on this deep dive. Hopefully the next time you successfully execute a massive project at work, you'll calibrate your own reflection better than a baseline LLM and actually take the win. Keep questioning the information around you, and we'll see you next time.